Pluto, the puzzling bantam planet, dwelling at the external scopes of our planetary group, is working up energy inside the cosmic local area. Late reports indicate a potential experience with Neptune, raising worries among researchers and space devotees the same. Eminent specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded alerts about the expected outcomes of this heavenly conflict. Yet, how did Pluto end up on a crash course with its far-off neighbor? And what could this vast impact mean for us here on Earth? We should investigate this unfurling event. Once thought about an undeniable planet, Pluto was subsequently renamed as a bantam planet because of its exceptional circle. Regardless of this transform, it proceeds to enrapture and draw in space experts. Late expectations from unmistakable researchers highlight a stressing closeness between Pluto's way and that of Neptune. These specialists alert against a possible crash between the two planets, representing a huge danger to Earth. Pluto's venture around the Sun is set apart by its unmatched qualities within our planetary group. Its circle ranges in broad 248 years, and since its revelation in 1930, Pluto still can't seem to complete a full insurgency. Adding to its interest is the profoundly circular shape of its circle, a takeoff from the almost roundabout circles of the significant planets. Furthermore, Pluto's circle is slanted at 17 degrees to the ecliptic plane, making its way more extreme contrasted with other planets. One eminent part of Pluto's circle is its crossing point with Neptune's way. For roughly 20 years in each circle, Pluto adventures nearer to the Sun than Neptune, resisting assumptions based on their separate situations in the nearby planet group. So why hasn't a crash happened between Pluto and Neptune? The clarification lies in the gravitational impacts applied by different planets. The assessment of Pluto's circle began not long after its revelation, introducing a astounding direction for space experts. In contrast to most of the planets whose circles adjust somewhat near the ecliptic plane, Pluto's unmistakable highlights incorporate a lofty tendency and a curved shape. The secret developed with the acknowledgement that Pluto's circle crosses that of Neptune. The strength of Pluto's circle in the midst of these complexities fills in as proof of the intricacies innate in space mechanics. The three-body issue in space involves grasping the development and gravitational communications among three heavenly bodies like Pluto, Neptune, and the Sun. This issue explains the multifaceted transaction of their ways and gravitational shafts. Terms like azimuth, vibration scope, libration, and the VZ-cable wavering add to disentangling this heavenly riddle. Astrophysicists declare that the south libration, answerable for keeping up with planets in their circles, assumes an essential part in the setting of Pluto and Neptune. This term connotes that when Pluto crosses Neptune's circle, it is situated at least 90 degrees away from Neptune, essentially forestalling potential crashes. Scope libration guarantees that when Pluto approaches Neptune or other giant planets, it is arranged essentially over their orbital plane, giving an extra layer of security against impacts. The VZK wavering makes sense of why Pluto's circle around the Sun shows up surprising, yet stays smooth over the long run. Notwithstanding obvious haphazardness in space, mathematical reproductions in the last part of the 1980s uncovered that notwithstanding steady properties, Pluto's circle is in fact turbulent, with minor introductory deviations prompting massive contrasts over large numbers of years. Anyway, Pluto's novel circle maintains strength over unbelievably lengthy timescales, holding tumult under tight restraints. Ongoing PC tests have improved our comprehension of how enormous planets like Neptune, Jupiter, and Saturn influence Pluto's way around the Sun. Neptune's special relationship with Pluto, finishing 3 circles for each 2 of Pluto, essentially adds to the solidness of Pluto's circle. Moreover, Jupiter's monstrous gravity applies a significant impact, while Saturn's influence, though more modest, likewise assumes a part. Through thorough tests, researchers have shown that the consolidated impacts of Neptune, Jupiter, and Saturn ensure the protected and stable development of Pluto in space for billions of years. These peculiarities are fundamental for keeping up with the request and consistency of divine developments in the universe. Without these systems, the sunlight-based framework would be inclined to more noteworthy disarray. Furthermore, capriciousness, possibly prompting impacts or launches from stable ways and causing expanding influences on other heavenly bodies. Getting it, Pluto's circle is especially urgent in the midst of conversations about a potential impact with Neptune later on. This information gives a more clear comprehension of the unique idea of the planetary group. Pluto's case highlights how apparently unsound circles can reach balance through the perplexing interaction of gravitational powers and orbital mechanics. Consistent observation and investigation of these peculiarities are imperative for acquiring a superior handle of our position in the universe. Investigating the profundities of space frequently uncovers the unusual nature of heavenly bodies. What's more, Pluto's circle fills in as a prime illustration of this unusualness. The idea of orbital bedlam clearly delineates the touchy reliance of a heavenly body's way on its underlying conditions. As shown in Pluto's case, even slight varieties in the smaller person planet's situation or speed can fundamentally modify its drawn-out circle. Programmatic experiences have been instrumental in aiding researchers comprehend how Pluto moves in space. By making little changes in these recreations, stargazers can see how minor changes can have a significant influence on Pluto's direction. In the late 1980s, these recreations uncovered a captivating part of Pluto's way. In spite of elements like AML and scope libration adding to its steadiness, Pluto's circle can in any case show unusualness. Even a minuscule beginning distinction in Pluto's situation or speed can prompt tremendous changes in its way over numerous years. In spite of this intrinsic turmoil, Pluto's circle remains stable for a particularly significant time frame, reaching out more than billions of years. This proposes that underneath its apparently whimsical appearance, Pluto's excursion around the Sun follows an organized request, foreseeing inestimable occasions. Particularly with planets like Pluto that have erratic circles, predicting their future ways is very testing. The innate capriciousness of these frameworks makes long-haul estimates dubious. Mathematical reproductions assist us with understanding and expect the future ways of heavenly bodies, but they likewise uncover the cutoff points of our prescient capacities. These models vigorously rely upon exact starting conditions and reenact complex connections. Even a small mistake can lead to fundamentally various results, making exact forecasts troublesome. The tumultuous nature of divine circles, such as Pluto's, helps us to remember the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our continued, limited understanding. Understanding the gravitational impacts of giant planets on Pluto's circle gives significant bits of knowledge into the more extensive dynamics of our solar system. Dynamics of the solar system. It demonstrates how each planet's presence and position can affect the stability and trajectory of other bodies in the system. Despite these complex forces, major astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such a collision, which seems unlikely given these intricate dynamics, is now a topic of concern. Neil deGrasse Tyson, a well-known astrophysicist, offers a special viewpoint on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet instead of a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is always evolving. Tyson sees Pluto's reclassification not as a demotion but as a necessary adjustment to our increasing knowledge about the various objects circling the Sun. His approach to celestial mechanics involves continual learning and adaptation. He views the complexities of orbits like Pluto as a reminder of how much more there is to discover in space. Tyson believes that the allure of these unknowns is what makes astronomy so captivating. Additionally, Tyson is aware of how space-related events and discoveries shape public interest in astronomy. He thinks occurrences like Pluto's reclassification and its unusual orbit are opportunities to capture the public's imagination and curiosity about the universe by discussing the dynamic and sometimes counterintuitive aspects of space mechanics. Tyson aims to foster a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe, working alongside other Scientist Tyson actively cautions the public about the potential danger of Pluto's unpredictable path. After extensive study of Pluto, he has raised concerns that the three-body problem might pose a real threat, suggesting that a collision with Neptune is long overdue. Additionally, Tyson emphasizes how such a collision could disrupt the balance of the universe and lead to catastrophic consequences extending to Earth. That a collision between Pluto and Neptune would be an unusual and catastrophic event in our solar system. This collision would release a massive amount of energy, likely breaking apart Pluto due to its smaller size and icy composition. Debris from the collision could scatter across the solar system, posing potential hazards for other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit depending on the specific details of the collision. Maio Kaku, a well-known theoretical physicist recognized for his work in string theory and science popularization, offers a unique perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide deep insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration, understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto. According to Kaku, can offer crucial insights for future space missions. This knowledge can assist in navigating the solar system more effectively, predicting potential hazards and planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, providing a blueprint for approaching and understanding distant worlds and discussing the physics of planets. Kaku often highlights the deep connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are linked to fundamental principles of physics. Kaku's work in theoretical physics, especially in string theory, aims to comprehend these principles at the most fundamental level. He suggests that studying the complexities of celestial mechanics like the orbit of Pluto can yield insights into the underlying laws of the universe. Similar to Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a significant event in astrophysics, offering a unique observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework replacing point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The collision of such magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extra conditions, a key focus in string theory. Additionally, the gravitational waves produced by the collision could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a remarkable example of celestial mechanics, showcasing both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. The universe holds many mysteries, and the three-body problem is just one of them. There are other potential disasters that scientists anticipate. While the chances of planets colliding in space are extremely low, it's not entirely impossible. The way Planets' orbits are influenced by various factors including gravitational interactions is explained by the three-body problem in some space systems like TRAPPIST-1 with 7 Earth-sized planets. The gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of system sys, like TRIST-1, collisions are not currently happening. Scientists closely monitor these systems to understand how planets influence each other's paths, particularly when they are near. This knowledge helps us comprehend the movement of planets in space. Rogue planets floating through space without orbiting a star introduce an additional, unpredictable factor. These planets, formerly part of a star system, are expelled due to gravitational disturbances or other celestial events, such as the close passage of another star or dynamic instability in multiple systems. Over time, these wandering planets can traverse vast distances, potentially reaching regions far from their origin. During their solitary journey, there is a possibility of them intersecting with other star systems. If one of these nomadic planets enters another solar system, there is a slight chance of a collision with a planet in that system. However, given the immense and predominantly empty nature of space, the likelihood of a rogue planet directly impacting another planet is very low. The vastness of interstellar distances and the scarcity of planets in open space serve as deterrents against frequent collisions. Additionally, rogue planets are relatively uncommon compared to the number of stars and planets in stable orbits, making such encounters even more improbable.